Okay, hello there. So we'll shortly discuss Kirchhoff's current law. So we were just taught this, so hopefully I can teach as well. So the principle behind Kirchhoff's current law is that current in is equal to current out, and so the difference between current in and current out should be equal to 0. As denoted here, I1 plus I2 plus I3, this is your current in, is equal to I4 plus I5 plus I6. That is your current out. And so you transpose all of these on the right side, your current out, you get 0. So let's visualize that. What do you mean by current going in? So current going inside a node. This is a node. A node is a point between like two branches. And then I'll use a term here, junction. Junction is a point between three branches, 3 or more. Like this here is a branch. I mean, this here is a junction. I mean, where there's three branches or 3 directions where a current can split, so to say. So let's look here. When putting this into equations, you can say that a current entering a node is positive. A current leaving a node is negative. What does this mean? So here's something to look at. We got this. This is your node, and we have these arrows. These are the direction of the current. So these here, I1, I2, and I3, they're going inside the node. Then we have I4 and I5, they're going outside of the node. And so if we put that into an equation, it is I1 plus I2 plus I3, because they're going inside, minus I4 minus I5. And of course, that is all equal to 0. Or like what we discussed, you can say I1 plus I2 plus I3 is equal to I4 plus I5. So, when doing KCL, we gotta assume directions. Okay, so here it says you have to have at least one current entering and one current leaving. As you can see here, one current is going inside the node, and you have 2 currents going out of the node. Okay, so here let's look at the circuit that I prepared. I'm going to be solving this. Let's assume its directions. So we're gonna use some concepts here. You can say that the current is that I1 is going in the node, I2 is going in the node, and then it comes back going towards the resistor, like the part of the resistor tree, which is your I3. So you can assume it in this way, to where I1 plus I2 minus I3. Of course, is this is negative because it is leaving the node. And then so remember the concept. I1 plus I2 is equal to I3. We just transpose I3. So look at this. Remember that currents in parallel, you add them. So it's more like the combination of these 2 currents make up this current. Let's assume it in a different manner. What if I want to say current 2 is going out of the node, current 1 is going out of the node, and current 3 is going in the node? How will that look like in the equation? In the equation, it looks like negative I1 minus I2 plus I3 equals to 0. And then you can see here, it's actually equal to they're all I1, the sum of I1 and I2 is equal to I3. So yeah, we use the basic concepts. Let's make it simple though. Let's keep it very simple. Let's use the first assumed directions that I used, where they combine the I1 and I2. Why did I erase that? I1 and I2 combined makes up the current of I3. So, alright, let's make up our equations again. So, I1 plus I2 minus I3 equals to 0. So what do we do from here? We don't have our current values here, of course. We're looking for current values. So let's remember, let's go back to Ohm's law. Remember, V equals IR. If you divide both sides by R, we'll be able to isolate our current. So like this, we have I, the current, is equal to V over R, voltage over resistor. And we can use this and substitute it with our currents. So I1 is V1 over R1 plus, so I2 is V2 over R2 minus I3, of course, is V3 over R3 equals to 0. So what do we do from here? What we want to do is, in algebra, we want to isolate one variable. How can we do that here? Now, we'll use some more concepts in circuits. Let's look at our circuit. We can see that our circuit can be composed of two parts. We got this part here with battery VA, and we got this part here, battery VB. So let's look at each individual part. So if you look at it, it's in series, right? You can see that this whole segment is in series. And remember, in series, voltages are added. Yeah, see, we're looking at V1, V2, V3. Yeah, we're just gonna look at our voltages. So voltages are added. You can say that V1 plus, wait, let me write it down here. V1 plus V3 is equal to our V total, which is VA. Again, we're just looking at this one whole segment. And we want to get V3. Why? Because you'll see later we'll isolate V3. We'll get our voltage tree, and then we'll get all of our values. So we want to isolate V3. We just transpose V1. So, we want to get V3 out of V1. So how do we do that? We're gonna substitute this into V1. So yeah, first we isolate V1. Sorry. That's gonna look like this gonna look like V1 is equal to VA minus V3. And then now we look at the other side. Remember, it looks like the exact same, right? Except with the exception that we're using V2 and VB. That will look like V2 plus V3 is equal to VB. And this is going to be V2 is equal to VB minus V3. So we have these now, and we're going to substitute it into the respective values. So V1 is VA minus V3 over R1 plus VB minus V3 over R2. Again, we substituted our values, minus V3 over R3. Okay, from here, we substitute in our given. Plug in our given. Our VA is 10 voltage. Is V3. Our R1 is 10 as well. Plus VB is 20 minus V3 over, oh wait, what's our R2? Our R2 is 20 as well. Oops. Hold on. Okay, 20 minus V3 over R3, which is 40. Oh yeah, is equal to 0. So, what do we do now? Well, yeah, we want to isolate VG, of course. How do we do that? There are many ways. I'll show you my way. I'm gonna show you because I think my way, for me, it is the quickest. But other people look at it in different ways. There are many ways to look at this. So you can get the LCD. You can do this manually, like this, and you do it for this, or you can do you can distribute the denominator, so it's gonna look like 1 minus V3 over 10. You get 1 minus V3 over 20, stuff like that. But me, when I tackle stuff like this, I wanna eliminate the denominators already. I wanna remove all the denominators. How do you remove all the denominators quickly? Well, we're gonna multiply the whole equation by values that can cancel out the denominators. Hence, we look here, our biggest denominator is 40. We can multiply the whole equation by 40. No? V3 over 10 plus 20 minus V3 over 20 minus V3 over 40 is equal to 0. I mean, of course, multiplied by 40. Remember, when you multiply the whole equation, both sides, whatever you do on one side, you do on the other side. But this is to 0, so it's just gonna be 0. If we do like this, we're gonna we distribute the 40. We cancel out this 40 because 40 over 40, 40 over 40, it cancels out. So we're just left with V3. 40 times 40, okay, 40, and then over 20. If you look at it this way, 40 over 20, that's just 2. So minus 2 times 20 minus V3, and then 40 over 10, that's 4. So give you 4 times 10 minus V3. And then this is easy. It's barbecue chicken from here. Let me put it up here. Times 10 minus V3 plus 2 times 20 minus V3 minus V3 is equal to 0. And this is very easy. So we distribute the 4. You get 40 minus, whoops, what the heck? 40 minus 4V3 plus distribute the 2. 40 minus, why is it doing that? Minus 2V3 minus V3 equals to 0. I mean, from here, you combine like terms. You can also just transpose the constants already, or you could factor out V3. Let's just do it straight from here. So 40 plus 40 is 80, and then minus negative 4V3, negative 2V3, negative V3. So 4, 2, 1, that is 7, and they're all in negative, so negative 7 v3 is equal to 0, and then it's gonna look like transpose 80, so negative 80 divide both sides by negative 7. What the hell? Divide both sides by negative 7. What the hell? And this, well, yeah, put this in the calculator, whatever. What is 80 over 7? It's equal to 11.43 voltage. This is your V3. Okay, so now that we know our V3, what do we do next? Well, our missing values are currents, remember? We want to look for I1, I2, and I3. You look here at the equation that we made. This is already your I1, this is your I2, this is your I3. Right? You know, because this is I1, I2, I3. We already put it down there. And since we already put it down there, we just need to substitute V3. So, I1 is equal to... Why is my iPad broken? I1 is equal to our VA, so let me just do this straight. 10 minus... Again, I'm looking here. Let me encircle it. I'm looking here. Or let me just do it like this. 10 minus our V3 is 11.43 over 10. Our I2 is equal to 20 minus 11.43. 20 minus 11.43 over 20. And our I3 is V3 over R3. I mean V3 over 40. Yeah, let's go straight. I mean 11 point... What? Hold on. 11.43 over 40. Yes. My bad. It's 12 a.m. Okay. Well, actually, you don't need to do this. You can do I1. Then once you get I1, you add it to I2. Because remember, it's I1 plus I2 equals to I3. This is just so that we can make sure, and so you can be reminded that we do have the formula for I3, which is V3 over R3. Well, this is a simple calculator. Yeah. So in my next video, I'll be doing KVL, which is the voltage law. I'll teach you shortcuts and stuff. So negative 0.143 amperes. Next we have 20 minus 11.43 over 20, which is 0.4285. If you add them, so minus 0.143, that gives you okay, wait, 5 minus 0.143 will give you 0.285 amperes. So let's try to see if that's correct. 11.43 divided by 40 will give you the same, 0.285, or I mean 0.286, basically the same thing, amperes. Fine, let me do 6. 0.286. Yeah, and we already solved the whole thing. We have here all our values. Did I take too long? I don't know. Thank you for listening.